the power goes out. Not slowly, not gradually. One moment everything works. The next moment, an entire city is dark. No warning, no explosion, no visible damage. And the most disturbing part is this: the power grid didn't fail because it was weak. It failed because it was doing exactly what it was designed to do. Today, you're going to understand why modern power grids, some of the most complex machines ever built, can collapse in seconds, and why that collapse is often unavoidable. If you enjoy understanding how invisible systems shape your daily life, subscribe now. This channel exists to explain the hidden limits behind the systems we trust the most. Let's start with the illusion everyone has. When people think about electricity, they imagine power flowing like water through pipes. If one pipe breaks, you fix it. The rest keeps working. But power grids do not work like that. They work more like a perfectly synchronized machine, where every part depends on every other part all the time. At every second, the grid must maintain a precise balance. Generation must exactly match consumption, not approximately. Exactly. If supply exceeds demand, frequency rises. If demand exceeds supply, frequency drops. And that frequency, usually 50 or 60 hertz, is the heartbeat of the entire grid. Everything depends on it: your phone charger, hospitals, data centers, air traffic control, all synchronized to the same invisible rhythm. Now here's the key problem. The grid has almost no storage. Electricity is produced and consumed in real time. If something suddenly changes, the system has only milliseconds to react. So what happens when a large power plant disconnects? Or a transmission line fails? Or a storm knocks out a critical substation? The balance is broken immediately. At first, nothing looks wrong. Lights stay on, motors keep spinning. But inside the system, the frequency begins to drift. That drift is deadly. Generators are designed to operate in a very narrow frequency range. Too low, and they risk mechanical damage. Too high, and they lose synchronization. So the grid protects itself. Relays detect the abnormal frequency and disconnect parts of the system automatically. This is not a failure. It's a safety feature. But here's the paradox. Every disconnection removes generation or load, which pushes the frequency even further out of range. That triggers more disconnections, and more, and more. This is called cascading failure. And once it starts, it spreads faster than any human can react. In seconds, entire regions can go dark, not because of one broken component, but because the system is trying to save itself. This is why blackouts feel sudden. The grid doesn't slowly collapse, it snaps. Now let's talk about load. Electric demand is constantly changing. People turn devices on and off. Factories start and stop machines. Air conditioners kick in during heat waves. The grid constantly adjusts generation to match these changes. But some loads are more dangerous than others. Large industrial motors, data centers, electric rail systems. When these loads disconnect suddenly, they don't just reduce demand. They change the electrical behavior of the grid. Voltage shifts, reactive power changes, stability margins shrink, and the grid becomes fragile. Now add weather. Heat waves increase demand dramatically. Cold snaps do the same. But they also reduce the efficiency of power plants and transmission lines. Hot air cools less effectively. Transmission lines sag. Resistance increases. The grid is being pushed harder, while becoming weaker. This is why many major blackouts happen during extreme weather, not because of storms alone, but because the grid is already near its limits. Now here's something most people don't realize. Modern grids are more complex and more fragile than older ones. Renewable energy changed everything. Solar and wind are clean and powerful, but they behave very differently from traditional generators. Coal, gas, and nuclear plants use large spinning turbines. Those spinning masses store energy as rotational inertia. If something goes wrong, that inertia buys time. Milliseconds matter. Wind and solar don't have that inertia. They connect through power electronics. Fast, efficient, but unforgiving. When disturbances happen, there is less stored energy to stabilize the system, which means failures propagate faster. This doesn't mean renewables are bad. It means the grid must be redesigned to handle them. And that redesign is happening, slowly. But the grid must work every second of every day. There is no pause button. Now consider this. Power grids are not centralized machines. They are enormous networks operated by multiple companies, agencies, and operators. Each section follows rules. Each operator protects their own equipment. When things go wrong, everyone does what they're supposed to do, and that's exactly what causes the collapse, because protecting individual components can destabilize the whole. This is the deepest irony of grid engineering. Local safety can cause global failure. That's why modern grids use controlled load shedding. Instead of letting failures spread randomly, the system intentionally cuts power to some areas, not because those areas failed, but to save the rest. From the outside, it looks like incompetence. From the inside, it's survival. Now think about recovery. Restarting a power grid is one of the hardest tasks in engineering. You can't just flip a switch. Power plants need power to start, which means some generators must be started without the grid. This is called black start capability. Only certain plants can do it. They start small sections of the grid, then slowly connect more and more components. Every step must be synchronized perfectly. One mistake and the grid collapses again. This is why restoring power after a blackout can take hours or days. The grid doesn't like being rebuilt. It likes being stable. So why don't engineers just build stronger grids? Because strength isn't the problem. Complexity is. The grid must be flexible, adaptive, and efficient. But flexibility reduces stability. Efficiency reduces redundancy. Redundancy costs money. Every improvement trades one risk for another. And that's the core lesson. Power grids don't fail because engineers are careless. They fail because they are pushed to operate near their limits, all the time. The grid is not a static structure. It's a live negotiation between physics, economics, and human behavior. Most days that negotiation works. Some days it doesn't. And when it doesn't, the lights go out. Not slowly, but all at once. That's the critical limit of modern power grids.